Hi there, I'm in the process at the moment of producing a second course called Design a CPU Supercharged. So the idea is we take the simple CPU and we do something useful with it. Now what I thought we could do is we could build a calculator. Now the reason for building a calculator is that this will ensure that we'll have to build up a number system onto the CPU. So right now the CPU doesn't really do very much, but if we wanted to build a calculator, then we're going to have to multiply, add, subtract, divide, take factorials. We'll have to find simple mathematical functions like the sine, the cosine, the tangent, the logarithm, that kind of thing. Now in order to do that, we're going to have some kind of number system. So we're going to start off with looking at a 1's complement unsigned, and then look at 2's complement unsigned, and we'll build up our add, subtract, multiply and divide in unsigned, and then we'll do it in signed, and then I'm also going to look at introducing it as a simple 8-bit floating point number system as well. So the calculator won't be able to do every single thing that you're looking for if you would get in a pocket calculator today, but it will have a decent subset with a decent range of numbers. Now the whole point of this is you'll be able to see how we build up a kind of number system, ultimately a floating point number system that will work on our calculator. And we'll also be able to see the trade-offs between creating new instructions, actually hardwiring the instructions, say for example a multiply or a divide function within the actual ALU, or using the tiny instruction set we have at the moment and then writing assembly language code for a multiply and divide. And in effect we could take this code and we could keep the code in the assembler debugger, or we could take the code and we could save the code into, in effect, a point in the computer that we could call the ROM. So this would in effect would be a microcode that we would continually call. So there's different ways of doing this, and it's useful building this up from this simple CPU because it gets you able to see the choices that are being made when people design the CPUs and the trade-offs. Also want to have a wee look at the idea of turning the control section into like a programmable logic array. So this would allow, instead of just having in effect one CPU, your CPU is programmable. You can get it to optimize it to run for certain things that you're doing. So say for example you were wanting to use the CPU purely as a signal processing unit, then or even a subset of that, you want to get to use it purely to work out fast Fourier transforms, then you could hardwire it in order to get it to do that quickly. And the idea behind this CPU whole course is you'll be able to see all these things and look at all the choices you've got from your actual CPU, rather than having someone just thrown a modern CPU architecture in your face, as what mostly happens. The idea is that we can, via trial and error, because I'm probably only a few videos ahead of you as you're watching the videos, so via trial and error we can build up something, and we can also then at some point compare it to an actual functioning CPU. So I've not decided which one yet, but I was thinking maybe the 8086 or 88, or maybe the Motorola 68000. So we'll go and we'll do that as well. We'll take a comparison, and we'll also look at all the extra types of addressing modes that you'll get in a modern CPU. So that's the direction I'm going, but the video here is really to show you where I've got so far, and I haven't got very far along the road, so I've put this video together and put it on as an impetus to me to get this up and get it running. Also in the resources section I've left the latest copy of the Logisim file, so you can open it up and have a look at it, and you can see how far I've got along. So I will periodically be updating that, and I'll put a new version on just so you can see where I've got to, and possibly I might replace this video as well. And I've also left a copy of the Excel VBA suppose this assembler and a debugger. So it's really a model of the CPU within VBA, and I've found it quite useful because instead of trying to design stuff directly on the CPU, I'm able to design stuff in that assembler. And if the assembler, it doesn't completely model 100% what's happening in the CPU, but it's close enough for it to be really useful when it comes to designing the little snippets of code. So let's go ahead now and I'll show you some of the code that I've designed, and if you like you can always have a look at this yourself, and if you see better ways of doing this, or if you think you can write some neat code to do stuff a lot better, then by all means go ahead and do that and give me a shout when you've done it. Okay, so thank you for listening to this, and I'll just listen to the rest of the video and I'll explain exactly where I am now. So if you go to the resources section, you'll see a file called design a CPU2. So this is the new CPU design that I'm working on at the moment. So if you were to go and open up that CPU test, you'll see this file here. Okay, this is the design. So let me just zoom in so we can have a little closer look at that. So ostensibly this is just the same design as the previous course. All I've done at the moment is just take the RAM out of the CPU. So originally the RAM and the clock and a few other sections here were actually inside this CPU section, but I decided to take it out so that the whole thing just looks a little bit more like in terms of a little computer. So we'd have a CPU here and a separate RAM, and we'd have the clock over here, and we can still load up the RAM the same way using this, what I've called here in effect as a hard drive. So it's like an external drive that we use to load up the program into the RAM, and we've still got all of the registers coming out here. We've also taken out the memory address register there as well. It's an extra one I've taken out. Now what I decided is that if we're going to use it as a calculator, we're going to just go and put all of the values for the calculations into one register. So all of the answers will come out into register R3. So there's no register R3 up here now, this is the register R3 here. Also, we don't want the answer to come out in hex, we want the answer to come out in a decimal value. So this register R3 is set up so we've got 3 decimal digits, so it's going to count up to 999, and this here is the section that I produced in order to change it from it changes it from a binary to a binary coded decimal, and then for the binary coded decimal it changes it so it can actually trigger or turn off the respective lights here. Now I thought whenever I went to design this it would be pretty straightforward, but it wasn't until I went to do it I realised that there was quite a bit involved in it. So I went online and I found a specific design, and I copied it and tweaked it and I made it work. Okay, so it took a wee bit of time and thought to get that little section there done, but that's available to us, and potentially we might extending that to maybe get a higher number of decimal places, but we'll work on that. That's something to come up in the future. So if you head into the resources section, there's another file there which has got the Excel spreadsheet, which is the assembler debugger, which is the this is a VBA approximation to the way the CPU works, and it's not 100% accurate, but it's decent enough and reasonable enough for allow us to actually write our code in here. So I think you've seen this here previously in one of the other videos there, but you can get in there and you can assemble this. So you can write the code here and you can assemble it. Now it's running slowly because I'm making this recording here, but I'll go through and it'll assemble it, and it'll put the assembly code actually here, and then you can go through and click on the debug, and it'll work through that one line at a time, and it'll put in all the values in the registers and all the flags. You can also work through the whole thing in a step. Okay, so you can step into it one instruction at a time. So we can click on step and it does one and it does the other one, and then we can also export it as well. So you can export the whole thing to the file called mysim, and when you export it to mysim you can load that into the CPU. and there's also a clear command here as well. So it's not absolutely foolproof, so you can break it. So if you were to, rather than write in data, if you write in like space data, then it won't know what you're talking about, okay, because it doesn't know what the space is. So there's lots of little things like that you could use to break it, but it's reasonably steady and it's okay. So also what I've been working on right now is if you get into the sample programs, down at the bottom there, there's a tab there called sample programs. So I've been working on these programs here, and I created one for the Fibonacci series just to get started on it, and I've worked out just a simple little program for doing unsigned 2's complement, which again I'll explain it in the next course when we go to do this if you don't understand that. And then there's a subtract routine here as well, which just does it's just a 2's complement subtraction, and there's a division here as well, so there's a 2's complement division, and also there's a little multiplication here which I'm just working on. So just multiplication is a repeated addition, so I'm just going to be putting that in there today. But the idea is over the next few days what I want to do is I want to be able to in effect call these functions within the assembler. So whenever I write, say for example I want to do a division, so right now it's dividing register R1 with R0. Okay, so register R1 with R0. So what I can do is I can put an R1 and R0, and then what I can want to do is just have like a log call function. So it would be, say, call, and I could call it sub, so it's called subtract. And when I call subtract, rather than me writing that code in again in here, it just goes and it'll pick out the code and it'll copy the respective code into the particular part here in this assembler, so that whenever we click on assemble, it will still just assemble the full code, but it just saves us from going and writing that code over and over again. So I'm just going to do the same thing for the add, subtract, multiply, divide, and there will be a factorial, and there'll be a power as well. So everything that I need in order to run what's called the Taylor series, because we're going to be working at all of the functions using the Taylor series expansions. So I'm going to do that this week, so I'll try and get that finished this week, and then next week what I want to do is I want to do the whole thing, or at the weekend I want to do the whole thing, not just for unsigned, but I want to do it for a sign. So basically we want to get negative numbers in this as well, but then of course it's only going to be an 8-bit machine, so I'm going to end up with just a very small set of positive and negative numbers, so 128 plus 128 to minus 127 I think it's going to be. So that's not going to be good enough, so what we want to do is we want to use a floating point, so an 8-bit floating point arithmetic. So that's my next thing, and to be honest I'm not 100% sure how I'm going to go and implement that. So I'll code it in at first and I'll check it out with the code, and also things like what we can do with this, we can leave all the code here within the assembler, or if we wanted to, if we open up this here, what we could do is we could actually save that code, and we could hardwire the code into a ROM so it's available here, so that whenever we write the instructions up, it could go and get that instructions from a ROM here, or it could just get the instructions directly from the assembler. So we'll just do it in the assembler. So what I'll probably do is I'll just do it in the assembler first of all to get it up and running and get something working on it. But I think the hardest thing for me is going to be the arithmetic, so doing the floating point arithmetic, so that, because that's relatively new to me as well. So well, I know how it works, but I've never had to actually go and implement any of it. Okay, so this is a first implementation of that for me as well. So I'll kind of learn a bit of this as I go along here as well. So that's where I'm at the moment, and it's once I get the arithmetic sorted out, and once I work out how we're going to do the floating point on the machine, I think that really is, as far as the calculator section, we've kind of killed it, because The rest of it, the implementation of a Taylor series expansion, once we get the code, starting able to write the code up, that'll come along quite quickly, and we should get something that works. But of course there will be a limited range because we're only going to be using an 8-bit floating point arithmetic, so there's not going to be a wide range of values here. But then of course you can look at extending it. We could, rather than do it as 8 bits, we could go and make the we could create instructions which will go and fetch 16 bits, and we could work on 16 bits. But that's another lot of design that you could potentially do, and that's the problem that I'm actually having at the moment, is that I've got too many ideas, there's too many directions in which I can take this whole design, and I'm going to have to try and limit it a bit in order just to get something done on it. Okay, so that's where I am just now, and I'll work on it over the next couple of weeks, and I'll come back to you and I'll let you know where I am with it. Also, if you want to, you can get into this in here and you can actually check the code running. So for example, you could do the division. So that divides, I think it's 12 divided by 2, which answers 6. So you can copy that, Control C, and you can stick it into the debugger. Go Control V, and then you can, I think that's everything, and you can assemble. Okay, let's see, make sure that all that's updated. I think it is. With one of my computers, it doesn't refresh automatically, and I have to go and refresh these myself. But in the other one, it's refreshing automatically, so you shouldn't have to do that actually. And I will change these lines as well because they're just functions. But I'm going to change these functions and I'll actually write them in the VBA code so that you can't overwrite any of this. So if you can click that and then click debug, and it will run through and it'll do the division. So you can see it going, it'll go 12, 10, 8, 6, and then it's the divisions there. It's going 1, 2, 3, 4, 5. So it's going to be 12 divided by 2, which the final value is 6. So that's the final value of 6 in register R3. And then you can export it, so I can go to SAC drive slash users slash ROS slash desktop, and you can put that wherever you want it. Okay, and it means that we've got that available to us, and we can come in here and we can just click on the reset simulation. We can click the reset button here, so it's a bit simpler than the previous design. So we can just click reset there, check that everything is reset, and then we can come in here, right click. So that's us right clicking down at the drive here. Maybe if I zoom in here you can see it a little bit better. Okay, so go to the drive there, so right click, edit contents, and you can get in and open up the file. Now the file on my desktop is called MySim. So that's it loaded up. So we should be 12 divided by 2. We get an answer 6 here if it runs as it's meant to run. So I just click simulate and tick enable, and there it's running through and it's loading up the values here. So you can go ahead and write some more code yourself if you want, or just play about with that code. And I'll get back to you in the next couple of weeks and I'll let you know the progress that I've made. So thank you for listening to this video, and I'll get you in the next update. Goodbye.